So we did an example of telescoping last time. Let's carry on with telescoping series. So if we think about a series, anytime we're trying to analyze convergence or divergence, we need to look at S sub n. S sub n is the sequence of partial sums, and that's what all the sequence practice with limits was, getting comfortable taking limits of sequences. And we use that information to create our sequence of partial sums for this series and then take the limit. And it seems like a fairly routine idea, find S sub n and take the limit. But it turns out there's only two series that we can actually find S sub n for, geometric and telescoping. So the scope in this class, only two series can we even find S sub n. So it's a very simple idea, but unfortunately we can't find S sub n except in these two cases. When we get to series that are not geometric or telescoping, we're going to need other techniques, which we'll start to do today. Lucky you. So the first thing we want to do is find S sub n for this series. So S sub n, we're going to start with k equals 3 for this series. So the first term here is going to be 1/4 minus 1/6. So there is our first term. Doesn't matter that it started with k equals 3. That's still the first term. Like the counter for the term number doesn't necessarily align with k. If k started at 1, then it also counts the terms in the series as well as generates the terms. And then our second term, we're going to plug in k equals 4, so we get a 5th minus a 7th. So this is the second term. And usually with a telescoping series, with the ones that we have in this book, usually it's enough to go to 3 terms in the front. You can go to 4 if you really are wanting to see the pattern, if you want to look more carefully at it. But 3 is usually enough to see the pattern. So now we're going to plug in, this was k equals 3, k equals 4. This is going to be k equals 5. So we get a 6th minus an 8th. So those are the first 3 terms. And now we need to stop at the nth term. And we're going to find the term before the nth term, which we call the n minus first term. So we want the sum of the first n terms. So now we have to know what the corresponding k values are. So let's think about this. This was k equals 3. This was k equals 4. This is k equals 5. So how do we get to k? How do we get to the term value from k? So if we're starting with the k value, k, we subtract 2 to get to this, or we add 2 to get to that. Either way. So we're going to add 2 to this, and we get n plus 1. Add 2 to this, and we get n plus 2. And so those are the k values. These are the n values. So we're plugging in the k values, and our next term, our n minus first term, is found by plugging in k equals n plus 1. So we plug that in right here. We get 1 over n plus 2 minus 1 over n plus 4. And then the nth term we find by plugging in k equals n plus 2. Did that see? So that's going to be an n plus 3 and an n plus 5. So that is S sub n. That's the sum of the first n terms. And now we can do the telescoping thing. There's going to be that collapsing of terms that cancel out. So when we look here, we're going to start from the left, and we see that the second part of this term cancels with the first part of the term after a skip. So second part, skip, first part. And that's pattern's going to persist. So this second part here, and if you want a fourth term, just to double check that you're seeing it correctly. So this second part is going to skip and then cancel with the first part over here in the dots. Similarly for this term, this second term is going to cancel with something in the dots. So on the front side, we see that this is not going to cancel, and this is not going to cancel. And it's second parts that are canceling with first parts after a skip. So now we have to sort of reverse the trend. And if we look here at the blue here, if we're going from the right to the left, the first here is canceling with the second after a skip. So first part cancels with second part, but after a skip. So first parts are canceling when we go the other direction. So this first part, we would skip and then cancel with the second part, so something in here in the dots. And then this first part right here is going to cancel after a skip with something in the dots. So we're going to have two terms that are left over at the end. We're going to have that one and that one. So we have a total of 4 terms for S sub n. So S sub n is going to be 1/4 plus 1/5 minus 1 over n plus 4 minus 1 over n plus 5. So that's S sub n. And you can check that your S sub n is correct. Like if we look at S sub 1, S sub 1 is this term right here. S sub 1 is just the first term. If we come down here and we plug in a 1, we're going to get a fifth minus a fifth. Those are going to cancel. And we're going to plug in a 1 there, and we get minus 1/6. And that matches this first term. So you can always double check that the formula you get for S sub n, you can check that it works. And we can simplify this a little bit before we take the limit of it. So these two, we can get a common denominator of 20 here. So it's going to be 5 over 20 plus 4 over 20. So that's 9 over 20. So our simplified S sub n will be this. So there's S sub n. S sub n, we have a formula for S sub n. That's awesome, because if we can find a formula for S sub n, then we can figure out what S is, if it exists. So S is, if it does exist, is the limit as n goes to infinity of S sub n, which is 9/20. Because both those two fractions at the end are going to go to 0. They have denominators that get infinitely large, so the fraction values get arbitrarily close to 0.
So, how do you know that n starts at 1?
N always starts at 1. N's counting.
Okay.
So n is counting the number of terms.
So is k the index?
K is the index, and n is the counting of the terms. So when k is 3, that's where we start here. There's the first term, so n is 1. So n is always going to count the number of terms.
Okay.
So S sub 2 will be when n goes from 1 to 2. S sub 3 would be when n goes from 1 to 2 to 3. S sub n, we're going to go 1 out to n, but then we have to correlate it with the k's, because the k is the index that generates the value. And so we see that k is always 2 more than n, or n is always 2 less than k. So we have to somehow figure out what the corresponding k's are going to be, because that's how we generate the term, by plugging in the k.
Yeah, could you explain that part actually?
How to get these two?
Yeah, and above them, the n minus 1.
Yeah. Well, this is just counting. So if you have to count to 5, you would go 1, 2, 3, 4, 5. If you have to count to n, you go 1, 2, 3, 4, ... n minus 2, n minus 1, n.
Yeah, minus part, why?
So this is the nth term. The one before it would be, just like if you had 5 terms, the one before it would be the 4th term, the one before it would be the 3rd term. So we repeatedly subtract 1 if we're going to move this direction in the term counter,
Okay, so
whereas we add 1 to go the other direction.
could be, instead of n minus 1, could we have add n and then the next one would be n plus 1?
Yeah,
Okay.
yeah.
It's just for the.
And so the definition of S sub n means n terms. If we had S sub 5, it would mean 5 terms. If we had S sub n plus 1, it would mean n plus 1 terms. So whatever this index is here, that indicates how many terms you need in your expansion. And so S sub n is always n terms, always starts with the first term, second term, third term, nth term is the last one. But then we have to figure out how it connects to the k's. And so when we see that the first term is generated when k is 3, the second term is generated when k is 4, we can see the pattern. That to get to the k value, we add 2, we added 2, we added 2. So here, to get to the corresponding k value, we'll add 2. To get to the corresponding k value here, we'll add 2. So that is then, the purple is what we plug in here to get the term value. Just like here, to get this term value, we plugged in k equals 3, we plugged in k equals 4 up here to get this one. To get this one, we're going to take n plus 1 and put it right in there for the k's. And then to get the last one, we're going to take the n plus 2 and put it in there for the k's. So when we plug in n plus 2 right there, we end up with n plus 3. Plug in n plus 2 there, we end up with n plus 5. That makes sense? And so if you think about the n as the counter and k as the generator, like if we want 5 terms, but if you started counting, or if you started generating your terms, so let's say this is k. If we started with k equals 4 right there, and this is n, this is counting the number of terms, what's the k value going to be here that we're going to plug in? 8. We're going to come through and say, okay, this term is generated when k is 4. We added 3 to n to get to this, so we're going to add 3, so it's going to go through like that. So there's like this shifting thing. And sometimes the index matches n, but not always. So if the index doesn't start at 1, then you have to make an adjustment to get the proper number of terms. So if we want, whatever for S sub n, we always want n terms, so whatever we see as the starting index, we just have to figure out what that shifting is. So we're shifting 2 to the right.
So if k was 0, then we would say minus 1.
Then we would end right there, exactly. So if k started at 0, then this would be 1, 2, 3, 4. We're going to be subtracting 1 to get to the final term. So in our scenario here, if this started at k equals 0, we would stop when we would stop that. So if we want n terms, if this starts at 0, we are going to subtract 1 right from that. So we would stop at n minus 1. We'd have 1 less.
Thank you.
Yeah. It's a little, once you understand that sort of shifting thing, that there's a correspondence, you just have to figure out what that correspondence is. But the main idea is that the definition of S sub n is we need n terms. If you started with k equals 1, then it's easy. K equals 1, and you would end at k equals n. But if k doesn't start at 1, you've got to figure out which direction you're adding or subtracting. We'll do a couple more for sure. All right, so, and everybody follows the limit. The limit's going to give us the value of the series. So this series converges to 9/20ths.
Sorry, just.
Yeah.
What is the difference between S of n and S?
S is the sum of the entire series. So S sub n is just the front n terms. So if we plug in n equals 100 right here, we will get the sum of the first 100 terms. If we plug in n equals 5, we will get the sum of the first 5 terms. If we want the sum of all infinite number of terms, we take the limit as n goes to infinity. So S is the sum of the series, the infinite series, whereas S sub n is the sum of the leading terms, the leading n terms.
So we use that to calculate the S of n? So
We use S sub n to calculate S. So if we can find S sub n, then we take the limit as n goes to infinity, and that will calculate the sum of the infinite series, or which we also call S. So if it exists, but it could be infinite. Could be infinite. So let's try another one. Okay, so it doesn't maybe look like a telescoping series because we don't see the subtraction. But if we use our laws of logarithms, we recognize that we could rewrite this so that there is a subtraction. We know that the laws of logarithms allow us to write that quotient like that. So that is our series. And now we're going to try to analyze whether this series converges or diverges. To decide if a series converges or diverges, we consider the sequence S sub n. So S sub n is always where we go when we want to decide if a series converges or diverges. So S sub n is the sum of the first n terms. So let's see. So this one starts at k equals 2. So when k is 2, we get our first term. That's going to be ln of 3 minus ln of 2. So this is our first term, which corresponds to k equals 2. And then we're going to go to our second term, which is going to correspond to k equals 3. So the second term, we plug in k equals 3 here, and we get ln of 4 minus ln of 3. So that right there is S sub 2. S sub 2 means add the first two terms together. S sub 3 is the sum of the first 3 terms, which will be found by going from k equals 2 to 4. So now we're going to plug in k equals 4. So we're going to have ln 5 minus ln 4. So that is the sum of the first 3 would be called S sub 3. And now once again, we want the sum of the first n terms. So the n minus first term is going to be here, and the nth term is going to be the last term that we're going to consider. To figure out what the value of the n minus first term is, we need to plug in the associated k. So now we look and we say, well, how do I get to k from n? Well, the first term, okay, if we add 1 to that, we get to the k value. Add 1 to that, we get to the k value. Add 1 to that, we get to the k value. So we're going to add 1 to this to get to the k value. So that's the k value that we're going to plug in to get the n minus first term. And then we plug in, we do the same thing over here. We add 1. And so that's going to be the k value that we substitute in to get the n minus first term and the nth term. Plug in those corresponding k values. So plugging in k equals n is going to give us natural log of n plus 1 minus natural log of n. And now we plug in n plus 1, and we're going to get natural log of n plus 2 minus natural log of n plus 1. So this is the nth term right there. And now we'll do our telescoping business. And it looks like I forgot a number here. This should be ln of 1 right there, right? Ln of 2 right there. Should be a 2. Because we're plugging in k equals 2 to get this first term. So plugging in a 2 there and there. So now let's analyze our cancellation pattern. So we'll start on the left and we'll move to the right. First part cancels with second part of next term. So going from left to right, we have first parts canceling with second part of next. First part canceling with second part of next. First part canceling with second part of next, which is in the dots. So on the front, we have negative natural log of 2. That's the only piece on the front, the only part on the front that's not disappearing. And now we go to the right, and we need to know what's the cancellation pattern going from right to left. It's easiest if we come back over here and establish it. So let's look at the greens. So if we're going from right to left, the second part here cancels with first part of the prior. Second part here cancels with first part of prior. So moving from the right to the left, it's the second parts that are going to cancel. This second part is going to cancel with the first part of the prior, which is somewhere in these dots. Same thing here. The second part is going to cancel with the first part of the prior, which is right there. So the only non-canceling term is that. So this tells us then that S sub n, we can write the formula for S sub n now. So S sub n, let's see, let's get a little more space in there. So that tells us that the formula for S sub n will equal minus natural log of 2 plus natural log of n plus 2. So that is our first goal, is to come up with a formula for S sub n. There is our formula for S sub n. And you can check. S sub 1 would just be this first term. S sub 1 is just the first term. So if we plug in 1 for each of these n's, we would get natural log of 2 with a negative in front, and then we would get plus natural log of 3, which is exactly what this is. If we plugged in a 2 here, we would get the sum of the first two terms. So if we plugged in a 2 right there, we get minus natural log of 2 plus natural log of 4. And if we look at the first two, oh yeah, the blues would cancel, and we'd get ln 4 minus ln 2. So that would match. Yeah?
How do you create k values?
The k values come from whatever starts right here. So this tells us that k is going to start at 2. And then we go to k equals 3. Then we go to k equals 4. And the question is, well, where do we stop the k values? The red ones are counting, just like we're counting our fingers. 1, 2, 3, 4. 1 term, 2 terms, 3 terms, 4 terms, 5 terms. And we want to stop at n terms. Well, if k is 2 for the first term and k is 3 for the second term, we see that k is always 1 more than n. So we just add 1 all the way down to the very end. That makes sense? So it's like this thing here is the shifting thing. We always want to, when we're counting, we start with 1. But k is used to generate the terms, and so we need to, if we want 5 terms, and k starts at 4, we're going to stop it at 8. And so we just sort of try to establish the pattern in front. K is 3 more than n, k is 3 more than n, k is 3 more than n, all the way down. So whatever that relationship is that you can see in the beginning, we apply the same relationship at the end. So if k is 1 more than n here, k is 1 more than n there. That makes sense? Yeah?
In that case, why wouldn't n plus 1 be in the same, or under the n minus 1?
Because when you add 1 to this, you get n minus 1 plus 1. The minus 1 and plus 1 cancel. That's didn't sound too convincing. If you have n minus 1 and you add 1, you get n.
Okay.
You see it?
Yeah, yeah.
And so here, when you add 1 to n, you get n plus 1. Here, when you add 1 to n minus 1, you're going to get n.
Oh.
You add 1 here, you get 4. You add 1 there, you get 3. You add 1 there, you get 2.
Yes.
You see it? So that's our pattern that we're going to use all the way through. In this case, is that we add 1. Let's try the next one where we have a starting value of 4, which is going to match sort of the one up on the board there. Oh, wait, let's finish this. Does this series converge or diverge?
Diverge.
So S, the sum of the infinite series, is going to be the limit of S sub n as n goes to infinity. So now we're going to take the limit of this as n goes to infinity. The natural log grows without bound, so that's going to infinity, and infinity minus natural log of 2 is still infinite. So this series is going to diverge. The sum is going to go towards infinity. So this diverges. But every finite series does converge, right? If you add a finite number of terms, it's going to converge. So if you plug in n equals 10 million, you get a number. If you plug in n equals 50 million, you get a number. If you plug in n equals, so the partial sums will always be equal to a number. A finite series always converges to whatever that finite number of terms adds up to. But the infinite series in this case goes to infinity. All right, let's try another one, see if we can get a handle on this. So this is an infinite series. We see that it goes to infinity. We want to analyze S sub n. S sub n is how you always analyze a series, if you can find S sub n. So this one starts at k equals 4. So we plug in a 4, and we get square root of 6 minus square root of 4. There is the first term. So n equals 1. That's the first term. Let me move that over a little bit so it's right underneath it. So there's the first term. That first term was found by plugging in k equals 4. I plugged in k equals 4 to get to that. So now we want to get to the next term. We're going to plug in k equals 5 to get the second term. So the second term, up here, we plug in a 5. So we get square root of 7 minus the square root of 5. So if we add those two terms together, that is S sub 2. S sub 2 means add the first two terms together. That's not what we want, though. We want to go out to n terms. So let's see. So then this is going to be, let's see, we added 3. So this is going to be a 6. So now we plug in a 6. We come up here and say, oh, okay, well, that's going to be square root of 8 minus square root of 6. Then we keep on trucking. We've got some dots in here. If you want to put a couple more terms to really see the pattern, you can absolutely do more. 3 is usually enough. If it doesn't feel like enough yet, then do some more. So then we have the n minus first term. We have the nth term. So this is going to be, let's see, we added 3 to get to the k value. We add 3 here, and when we add 3, we get n plus 2. And when we add 3 here, we get n plus 3. So the n minus first term will be found by plugging in n plus 2. So we go up there, we plug in n plus 2. So n plus 2 right there, we'll get n plus 4. Minus, we're plugging in n plus 2, so that's going to be that. Then we have one more term to plug stuff in. So to get to the nth term, plug in n plus 3, so we're going to have an n plus 5 right there. Minus, plugging in n plus 3, that's just a k, so we get an n plus 3 here. So so when n is 2, we add the first 2 values. When n is 3, we add the first 3 values. When n is n, we're adding the n terms together. Now we establish the cancellation pattern. So if it's a telescoping series, there's got to be some cancellation. So we start over here, and we see that first with second after a skip. So going from left to right, first parts are canceling. So this first part is going to cancel with the second part after a skip, so somewhere in the middle there. If you drew out a bazillion terms, you could see the pattern more clearly, but we don't need to draw out that many. So first canceled with second after a skip, first canceled with second after a skip, first is going to cancel with second after a skip, and it's going to be gone. So all of the seconds are going to cancel except for these two right here. These are sticking around. Those are the only two on the front that are not canceling out. Now we go right to left, and we establish the pattern by looking in the front. If we're moving from right over to left, that second is going to cancel with a first after a skip. So when you're moving from right to left, second parts are canceling, not first parts. So this second part of this term is going to cancel with the first part of the term over here after skipping a term. This first part is going to cancel with a second part after skipping this. So on the tail end here, that and that are still there.
Wait, no.
Did I cancel wrong?
Yeah, so the.
Oh, I did cancel
Yeah.
wrong. Yeah, thank you. Let me say it again. So when we're going from right to left, second parts are canceling with first part after a skip. So second parts are canceling. So I shouldn't have this red one there because it's second parts that are canceling. So that second part cancels with a second part after a skip. Oops. Yeah. So the two pieces that stick around at the end are first parts, whereas the two pieces that stick here are second parts. So going left to right, first parts are all canceling. Going this direction, second parts are all canceling. And so that gives us a nice formula for S sub n. So S sub n will equal, from the front, we have minus 2, square root of 4 is 2, minus root 5. Then we come down here, we have plus square root of n plus 4. And plus square root of n plus 5. So that is our S sub n. Now, again, you can check it to make sure that you didn't, like I would have noticed if I was just doing this blindly and I picked the wrong term there, I would notice it right here, because I would say, hey, let's check. S sub 1 is going to be this term. S sub 1 is the first term. If you plug in S sub 1 right here, what happens? Okay, plug in a 1, you'd get square root of 4 here. This would be negative square root of 4, so those would cancel, and you're going to get, let's see.
No, it's.
If you plug in a 1, you get a square root of 5. Duh. Plugging in a 1. If you plug in a 1 for n, 1 right there, 1 plus 4 is 5, you're going to get plus root 5, minus root 5, those cancel. Plug in a 1 right there, you get negative 2 plus square root of 6. That's what we have here, negative 2 plus square root of 6. And so if that doesn't match your very first term, when you plug in 1, then you know you screwed something up at the tail over here. Now, so once you establish your pattern over here and you build your S sub n, plug in 1 and just check that it matches that first term. If it doesn't, then you made a mistake canceling. So there's our S sub n. What about S? Does this series converge? So the limit of S sub n as n goes to infinity is infinity, because those square roots grow without bound. So this series also diverges, because the limit of that's infinite. All right, question on any of the steps there? Yeah.
So if we want to look at the last three terms, then we'll start with n minus 2, and the next one is n minus 1, and then n.
Yeah, so n minus 2. If we wanted to put a third term at the end here, we would plug in, what would we plug in for k?
One.
Plus 3,
N plus 1,
1. Oh,
right? Because we add 3. So if we add 3 to n minus 2, n minus 2 plus 3 would be n plus 1.
I just don't really understand how can you cancel the term.
So the terms, so you see that the plus root 6 and minus root 6 cancel.
Yeah.
Yeah. So what we say to ourselves is that we need to somehow verbalize what's happening. And the way I think of this is that each term has a first part and a second part. So the first part of this term is canceling with the second part of that term. And as we continue from left to right, that means that that pattern is going to stay. This first part right here is going to cancel with the second part over here. And we didn't write that term out, but if we wrote the fourth term, it would be canceling with the second part of the fourth term. And so going from left to right, it's these first parts that are all going to cancel. Same with this. This first part is going to cancel with a second part that's a little bit further down the road. So it's got that telescoping collapse nature to it. So when we're going from left to right, all of these firsts are canceling. And this second is canceled, so the only 2 seconds that stick around are these two. So in the middle, all the firsts and seconds are going to cancel. But at the front, we have 2 seconds that are sticking around. And when we go the other way, it's the second parts that cancel. This is going to cancel with something that's over here to the left, somewhere over there. And similarly, this term here, the second, is going to cancel with something that's over here. But these first parts aren't going to cancel.
How did you know they were going to cancel if you didn't write them?
They
Be-
cancel with terms later.
Yeah, because the only way these could cancel is if there was another term over here that had a second that would cancel with this first. Right, when we're going from right to left, this second cancels with a first that's over here in front. This cancels, like if we had another term here, this first would cancel with whatever the second part of this term would be. So if you wanted to, you could write out like 5 terms on the front, 5 on the back. If you're not seeing the pattern exactly with this minimal number of terms, you could write out 5 on the back, 5 on the front, and you could see it maybe more clearly. And we could do that for the next one. We could write out more terms and see. So somehow we have to just sort of figure out what the pattern is. I guess I don't have another example of a telescoping. But if you want to, you could write out more terms and see it. So let's just talk about this for a moment. This is an interesting idea. So you all know from Calc 1 that one of the greatest strengths of Calc 1, one of the applications that you see widespread everywhere, is that you can now find the area under a curve. So you can find the area of a shape that is not geometric, that's not like a triangle or a rectangle or a polygon of some sort that has a formula to find the area. All right, that's what you learn in Calc 1, how to find the area of shapes that have curved boundaries. You can find the area under a parabola. Well, prior to calculus, infinite series were already understood prior to calculus, And you can find the area of a parabola, of a parabolic region by using an infinite series. It turns out that there is this relationship that if you take your parabolic region and you bisect it and create this isosceles triangle, got that, then you take and bisect each of those two intervals and you create these other two triangles that are, we're going to call them a sub 2. We're going to exhaust, they call this the method of exhaustion. Oh, somewhere in here, yeah, method of exhaustion. We are going to exhaust all the area underneath the parabola by continuing this process. So right now we have most of the area with these three triangles, two a sub 2's and an a sub 1. Well, then you can bisect those intervals and create 4 more little tiny triangles that are sliverish triangles. And you can imagine that you just keep building these triangles until you exhaust the area of what's inside that parabola. The part that makes it amazing, and you can calculate this, I'm not going to do it because it's a pain in the neck, you can show that the area of this second triangle, these a sub 2 triangles, is exactly 1/8 the area of the first triangle. So when this was first discovered, you'd have to draw something very accurate and very large so you can kind of see what's going on. Because once you bisect each of these intervals, right, you're going to have 4 triangles, 4 extra triangles, and then if you bisect those subintervals, you're going to end up with 8 more triangles, and you just get more and more and more triangles until you exhaust the whole area. And the part that's amazing, this is pretty easy to show, that the second triangle is 1/8 the first triangle, but then that pattern also continues, that the a sub 3 is 1/8 a sub 2. So the triangles are getting tinier with the same factor of 1/8 as the multiplier. And so it turns out that we're going to have 2 a sub 2's, 4 a sub 3's, 8 a sub 4's, 16 a sub 5's. So we have all these bazillions of triangles. Well, a sub 2 is 1/8 a sub 1, so we replace a sub 2 with a sub 1 over 8. And similarly, a sub 3 is 1/8 a sub 2, which is 1/8 a sub 1, so you can replace a sub 3 with a sub 1 over 8 squared. On down the line, you have this pattern that the next triangle is 1/8 as big as the prior triangle. This is an infinite series. That is geometric. That is a geometric infinite series. So if I simplify here, so I cancel out a 2 here, cancel out the 4, cancel out an 8, cancel out a 16, when you reduce this to that, you should be seeing that this is a geometric series with common multiplier. What are you multiplying from one term to get to the next? 1/4. So your R value is 1/4. You do continuous multiplication by 1/4. So this is a geometric series with R equals 1/4. And the very first term in this geometric series is 1. And that's all we need. We saw last week that if you have a geometric series, if you know the R value and you know the A value, you plug it into S equals A divided by 1 minus R, and we get 4/3 multiplied by whatever the starting area was of that isosceles triangle, depending on the parabola you chose. So for example, if we choose this parabola, 1 minus x squared, the blue parabola, then that triangle that we build, this isosceles triangle, is the black triangle, which has area half base height, which is 1. And according to the method of exhaustion, we are going to take whatever that initial area is and multiply by 4/3. So the initial area is 1 for the black triangle, multiply it by 4/3. That's the area under the parabola according to the method of exhaustion. Well, let's go to Calc 1 and double check. We can find the area by integrating the function, and I use symmetry. I said, oh, let's integrate from 0 to 1, and then double it. Well, yeah, of course, we're going to get the same exact area, 4/3. So the interesting thing is that these infinite series are often going to have applications for problems that you could do a different way, but you know, before there was TV and things, this is what people sat around doing, right? Solving weird math problems, or praying, or both.
About reading.
Yeah, maybe some reading. You didn't travel very far. The average person, what, went like within 10 miles at most from their place of birth? That's a lot of downtime. Way more downtime than we could ever imagine. Okay, so that's just an interesting example for an application of infinite series. Infinite series are going to show up everywhere. I already talked about it in the calculator. Every time you do a computation in your calculator, there's an infinite series involved. So let's talk about some properties of infinite series. And these properties should seem pretty intuitive. So if we have an infinite series that converges to A, and then we multiply that series by a constant, you end up with a new infinite series. Right? If you take every single term and multiply it by some non-zero number C, then you have a new infinite series, and that new infinite series is going to converge to what the other infinite series converged to, and you just multiply by the C value. You know, it's just like factoring out a constant. So if you've got a series that converges, you multiply it by a constant, the new sum is the old sum multiplied by C. Now if you have a series that diverges, and you multiply by a non-zero constant, that series still diverges. There's no way to take a divergent infinite series and multiply by a constant and make it converge, unless you multiply by 0. There's no way you can multiply by a negative or a positive number and force a divergent series to all of a sudden converge. Okay? So if it's diverging, it's diverging. If you have two series that converge, say to A and to B, and you create a new series by adding them together or subtracting them, you get a new series in each case, whether you add or subtract, and both of those are going to converge to what you would expect. If you have a series that converges to A and a series that converges to B, if you add the two together, the new series converges to A plus B. So very intuitive properties, kind of like our limit properties. Similarly, if you have a series that diverges and another series that converges, if you add them or subtract them, you still have divergence. A divergent series cannot be sort of fixed. So if you have a divergent series and you have a convergent series, you add them together, you still have divergence. You subtract them, you still have divergence. Right? That convergent series can only subtract off a piece of your divergent series. Your divergent series is going to dominate. And then this we've already talked about. If you have an infinite series and you chop off the leading terms, so we have our infinite series that starts at 1. We have the same infinite series, except we're going to chop off the leading terms. We're going to start and just look at the tail of it. Both of those are going to converge or both are going to diverge. If you chop off the leading 100 terms, doesn't affect convergence or divergence. Chop off the first 1,000,000 terms, doesn't affect convergence or divergence. Now they would converge to different numbers if they both converged, right? Because this one has less terms in it. Less terms that you're adding together. So it's going to converge to a different number, but it still will converge if the entire one converges. Just converge to a different number. So when you're thinking conceptually about convergence, the leading terms of an infinite series, so those are the terms in the beginning with small indices. The tail is where the terms have very large indices. It's the tail that determines convergence or divergence, but it's the leading terms that sort of dominate what the series converges to. Because when we look at the tail of an infinite series, the terms are approaching 0. So when you go way out in an infinite series that converges, the terms have to approach 0. And so the tail doesn't have a lot of substance to it. Like if you're looking at the value of your infinite series, the value is mostly determined by the front terms. That's where the terms are biggest. Because the tail, the terms have to be going to 0 or the infinite series would diverge. So the terms have to be going to 0 and they have to be going to 0 pretty quickly for the series to converge. So when you're thinking in your mind, the leading terms are sort of indicating what it converges to, if it converges, but the tail is what is indicating whether it converges or not. And the tail has to go to 0 fast. But the leading terms are going to dominate whatever it converges to. All right, so Koch snowflake. This is, we're not going to have a problem in the homework about this, but this is probably one of the first examples of a fractal you'll see. And it's one of these interesting, as you go on in calculus, you start to encounter these shapes, these objects that have interesting properties that can seem a little bit mind-blowing. So the Koch snowflake is found by this iterative process where you chop out the middle third of each side and you create an equilateral triangle, and you keep doing it again and again and again. You have this fractal. And it turns out, probably not a surprise, that the area is finite. You can draw a circle around it, so it should be pretty intuitive that the area is finite. You can't add area. If you draw a circle around it, that's going to indicate that it's got finite area. But the perimeter on this is going to be infinite. So the length around the outside is going to be infinite because the number of sides are increasing, and there's positive distance on each of those sides, and it's increasing in a way that you're going to have an infinite perimeter. And so if you're curious about these types of interesting examples, I created this little table here where we can see the formula for the perimeter after n iterations of this equilateral triangle replacement of the middle third of each side. So that is the general formula right there for the perimeter. That's a geometric series. The R value is larger than 1. We know that with the geometric series, if your common ratio is larger than 1, the series or the sequence, let's think of it as a sequence in this case, the sequence is going to diverge. If the R value is larger than 1, this is going to diverge. So similarly, if you look at the triangles, area, this is representing the area after the nth iteration, or this is the area of the nth triangle. And if you want the total area, you have to add up all the the values for all the n values. It turns out that the area is going to be a geometric series with an R value less than 1. So you're going to end up with a finite answer. So that's going to be the area of the triangle. And the perimeter is simple because we just take the limit of this, and that's going to be infinite. So it's an interesting exercise to just sort of think about how you would compute all these little pieces of the Koch snowflake. And when you get into Calc 3, you have other objects that's the same type of thing that will have finite volume but infinite surface area. So you will encounter these crazy objects more and more as you go on.
That's the same with Gabriel's horn, right?
Gabriel's horn is one of those objects. Yeah, it's got finite volume but infinite surface area. So we can see that with symmetric objects in three-dimensional space. When you get into Calc 3, you can talk about objects that are created not through rotation. Calc 2, we can get at some three-dimensional objects if we rotate, because there's some symmetry there. Okay, so Chapter 10, Section 4. This is probably the most important concept with infinite series. Very simple. It's called the divergence test. It says, if the infinite series converges, the limit of a sub k has to be 0. So this is saying that the only way series can converge is if the terms that you're adding together get infinitesimally small. All right? It's the only way. You have to be adding numbers that are very close to 0. Like if you added 0.1 to itself forever, you get infinity. You have to be adding terms that are getting negligible out in the tail. So if a series converges, the only way that can happen is if you're eventually adding something very, very, very close to 0. So that's what this says. If the series converges, the sequence of terms, not the sequence of partial sums, the sequence of terms must be going to 0. Equivalently, if the limit of a sub k is not 0, the series has to diverge. If the limit of a sub k is 1, then in the tail of the series, it's like you are adding 1 plus 1 plus 1 plus 1 forever. It's got to diverge. The only way a series, an infinite sum, can converge is if the terms go to 0 fast. If the terms don't go to 0 fast, it's like blowing up a balloon, eventually it's going to pop. The terms have to go to 0 fast. So they have to go to 0. If they don't go to 0, the series diverges. The divergence test cannot be used to figure out if a series converges. The divergence test can find egregious divergence, or it's inconclusive. It cannot find convergence. It finds egregious divergence. And by that I mean, if the limit of the terms aren't even 0, there's no question, the series diverges. That's egregious. If the terms don't even go to 0, hands down it diverges, you're done. The question is when the terms go to 0 and it still diverges. That's the hard thing. If the terms go to 0, that means it might converge or it might diverge. Just like we saw with improper integration. If the tail is shrinking down, you've got the unbounded region, it mattered how fast the terms went to 0. So just going to 0 is necessary. They have to go to 0, but it's not sufficient. It's not enough. We need more. So the divergence test is only going to show us possibly divergence, and otherwise it's inconclusive. So one thing we want to understand is what the contrapositive means, because that's what this is up here. So when you have a statement that's true, so this says, if the series converges, then the terms go to 0. That's a statement. That's if P, then Q. If that's true, then logically the contrapositive is also true. The contrapositive says that not Q implies not P must also be true. So the contrapositive up here is, it's equivalent, that if the limit is not 0, then the series is not converging. So that statement right there is the contrapositive of the initial statement. And you can think of it, there's this clever idea here, which if we think about Paris, France, the city of Paris, France, then this statement is true. I live in Paris, therefore I live in France. Talking about Paris, France, not other Paris's, right? So we're thinking about Paris, France. If you live in Paris, France, then this statement is true. I live in Paris, therefore I live in France. The contrapositive would be, I don't live in France, therefore I don't live in Paris. That has to be true. Assuming we have just one Paris, Paris, France. The converse is not necessarily true ever. The contrapositive is always true if your initial statement is true. The contrapositive is always true. The converse is not necessarily true. Converse says, I live in France, therefore I live in Paris. That's the converse. That is false. Converse is usually false when we're dealing with these things. So contrapositive, always true. Converse, not necessarily true, usually false. So that's a good one to just sort of have in your mind to understand these two logic concepts of contrapositive and converse. So let's do one example and then we'll take our break. We've got this infinite series here. The very first thing, if someone hands you an infinite series, the very first thing you should say to yourself is, what's the limit of a sub k? Because if the limit of a sub k is not 0, the series diverges. That's the very first thing you should think about. You don't necessarily have to write it down unless it asks you to, but like whenever someone hands you a series, that's the first thing you should at least think about. And if the limit of a sub k is obviously 0, then you have to do more work. So here we take the limit of a sub k, so the limit as k goes to infinity of a sub k. And what is the limit of this a sub k? What's the limit of that? 1, right? Powers of k match, so we take the quotient of leading coefficients. That's the algebra way. You could also say L'Hopital's rule and take derivatives top and bottom, a few times. Or you could divide by the highest power of k. Dividing by the highest power of k is probably the most intuitive way. But you could do it the algebra way, you could do it the calculus way. That limit is 1. This is not equal to 0, therefore divergence. So instantly, if the terms don't go to 0, the series has to diverge. So that is the divergence test. It can find egregious divergence. This is egregious because in the tail, you're adding 1 plus 1 plus 1 plus 1 plus 1 plus 1, which goes to infinity. So that has no chance of converging if the terms don't go to 0.
So what does that 1 mean here?
This one,
Yeah.
that means that if you go far out into the tail of the series, you are adding numbers together that are super close to 1. 1 plus 1 plus 1 plus 1. The a sub k is telling you what the value of each term in the series is. So as k gets bigger, this gets closer and closer and closer to 1. So way out in the tail, you're adding 1 plus 1 plus 1 an infinite number of times, which means divergence. The only way a series can possibly converge is if you're adding terms that are super close to 0 out in the tail. So this one, you're adding 1 to itself repeatedly, which means divergence. So if a sub k's limit is not 0, you know instantly it diverges. Because if you add the same number to itself an infinite number of times, you have infinity. 0.1 plus itself a million times, well, plus an infinite number of times is infinity. 0.000001 added to itself an infinite number of times is infinity. Doesn't matter how small that number is, if you add it to itself an infinite number of times, you get infinity. The only way you can add an infinite series together and get something finite is that the terms go to 0. If terms aren't approaching 0, then no chance.
Sorry, if we get partial sums of this, I'm just trying to understand the difference, then what would that...
So this is an infinite series where we can't find S sub n. This is not telescoping and it's not geometric. So this is our first test for non-geometric and non-telescoping. So this is our first series where we can't find S sub n. There's not going to be a formula that we can create for S sub n and then take the limit. So this is our first example where we need to come up with another approach.
So if it were a telescopic relationship or geometric, then we would get 0?
No, if this was geometric or if it was telescoping, the limit of S sub n would be infinity.
What would be the limit of this?
Limit of S sub n would be infinity here. So if you have an infinite series that diverges and you could find a formula for S sub n, its limit would be infinity. Because this series is just going to go to infinity because we're adding 1 plus 1 plus 1 plus 1. So if we could find a formula for S sub n, its limit would be infinity. So any series that diverges to infinity will have an S sub n that has a limit of infinity. We just can't find S sub n in this case. So this is the beginning of the rest of the story. If you don't have geometric, you don't have telescoping, now we need to come up with other ways to analyze. So this is our first test, first of 10. Well, we already had geometric and telescoping, so there's 7 more. So this is our third test. All right, let's take our 10-minute break, and then we'll look a little bit more at the divergence test. Okay, so divergence test, again, it's our first test. other than, so we have to just sort of keep loose track. We started out with geometric series, started out with telescoping. Those are our first two. And we know how to tell if those converge or diverge. We find S sub n and take the limit. Okay? And we had some stuff that boiled down for a geometric series. If r was less than 1, it converged. If r is bigger than 1, it diverges. But that all boiled down to finding S sub n and taking the limit. Bless you. So now, when we don't have geometric or telescoping, our first idea is this divergence test. And so again, it's only finding egregious divergence. And by that, what I mean is that for example, the harmonic series, which we're going to look at later today, is an example of a divergent series. So this series right here, the harmonic series, this diverges. We're going to prove that later today. So that diverges. So this has terms that are going to 0, and we also saw this when we integrated, when we did the improper integral, right? We already found that. So the harmonic series is going to diverge, even though the terms going to go to 0. They just don't go to 0 fast enough. Like if you had something like this, the terms do go to 0 fast enough, and this is going to be some number. That's going to converge to a number. And so that was very similar to the improper integrals that we did that look like this, 1 over x squared. That converged. This one is going to converge to some number. So that's going to be finite. So what we're trying to establish is that, okay, well, the terms definitely have to go to 0. If they don't go to 0, we have divergence. But then the bigger question is, well, are they going to 0 fast enough for convergence? These are not going to 0 fast enough. So here, the divergence test is inconclusive because the limit of 1 over k as k goes to infinity here is 0. So therefore, the divergence test is inconclusive. And if the limit is 0, you might have convergence. We have to do some other testing. But if the limit is not 0, you definitely have divergence. So that's what we're sort of looking at right here. The limit's not 0, so we definitely have divergence. So now we're going to take a look at this one. So we're going to take the limit k over natural log of k as k goes to infinity. And the first thing I notice is that this is indeterminate, just like the one up here is indeterminate. So when something is indeterminate, you have to do something. So with the top one, I divided everything by the highest power of k, and then we reevaluated. For this one, that's not going to work. Let's use L'Hopital's rule. So L'Hopital's rule says that if you have a ratio of functions, you can take the ratio of the derivatives. So we're going to take the derivative of the top function with respect to k, derivative of the bottom function with respect to k, simplify and reevaluate. So let's simplify this, and then reevaluate, and what is that limit?
Infinity.
That's infinity. That's not 0. This one is super egregiously diverging. Okay. The next one. Okay, why don't you all try this one? So try to take the limit of this. And I know you're going to have to remember something from the past on how you differentiate a exponential with non-base e. Let's see if you can remember it. So that one is, again, it's indeterminate. You have infinity over infinity. Polynomials go to infinity. Exponentials go to infinity. Should I write those in red? What is your hunch? Is your hunch that the limit is 0, or is your hunch that the limit might not be 0?
0.
And that hunch is hopefully based on the concept of growth rates. The type of function in the denominator is, what's that function categorized?
Exponential.
Exponential.
Exponential. And the one in the top is a polynomial. And which function grows faster, exponential or polynomial? Exponential grows faster than polynomial. So the denominator dominates. It's going to go to infinity faster than the numerator. So your hunch that we're trying to build your intuition for, like a lot of times math should be confirming your intuition. That's what we want to try to build your intuition so that doing the math is just confirming that. So this bottom goes to infinity, the top goes to infinity, but the bottom's an exponential. It goes to infinity faster, so this limit you should expect to get 0. But now we have to do the math, so that's what you're doing now. So you're taking your derivatives, and one derivative might not be enough. So when you differentiate the numerator, you get 2k. Anyone remember what the derivative of the denominator is? Derivative of an exponential?
It's the same.
Start out with itself, and then multiply by the derivative of the exponent. The derivative of the exponent is just 1 though. But if the base is not e, you also have to multiply by natural log of the base. Okay. So if the base is not e, and you're differentiating, you have to multiply by the natural log of the base. This is still infinity over infinity, correct? We still have an indeterminate form, so we can apply L'Hopital's rule again. Now, the limit at the top is 2. All right, so we had a power of 2. We had to differentiate twice to get to a constant. Constant is now a basic limit situation. Now in the denominator, the derivative of this denominator, the derivative of 2 to the k is once again 2 to the k multiplied by natural log of 2. So we're going to have natural log of 2 quantity squared now down here. And now we have a basic limit. Basic limit is where the top is constant, the bottom is going to infinity, so those fractions are going to 0. Right? So that's one of our basic limits. When the top is constant and the denominator is growing without bound, the limit is 0. So therefore, does this converge, diverge, or inconclusive? Inconclusive. Inconclusive. The divergence test cannot give convergence. The divergence test either finds divergence or, who knows, do some other testing. So divergence test is either diverges or don't know. Inconclusive. The divergence test cannot find convergence. The divergence test only finds egregious divergence. Now intuitively, building on those intuition ideas, the exponential function grows much faster than a polynomial function. So your hunch should be that the series probably does converge, because dividing by an exponential is going to force the fraction values to go to 0 pretty darn quick. All right? So your intuition should be that this is probably going to be a convergent series. Now, this is not a standard series, so we are not going to be able to even estimate what that converges to unless we start doing some harder math. So all we're going to be able to say, even when we get to our next test that's going to show that this converges, we are not going to be able to find what it converges to. That's a hard question. What does it converge to? It's a very hard question. Unless you have a telescoping or a geometric. If you have a telescoping or a geometric, you can find the actual sum of the series. For most series, you can't. All you can say is that it converges or it diverges, and if it converges, we have some estimating tools, but that's hard. That's much harder math. Okay, now this one. Once again, we want to take the limit of a sub k. That's the first thing we think about in our mind. And if the question is about divergence tests, then you have to write down some math. If the question is more general and it just says, does this converge or diverge? In your mind, you would at least run through this process. You don't necessarily write it down every time, but this is one that is infinity over infinity. We have both the numerator and denominator growing without bound. We can't take the derivative of k factorial. That's a discrete function. We don't have any way to take its derivative. So we can't just say, hey, let's take 3 derivatives like we took 2 derivatives here. So we can't do that here. We don't know the derivative of k factorial. Until you learn of a totally wacky function called the gamma function. The gamma function generalizes the factorial so that you can take factorials of non-integers. So the factorial function is that multiplicative function. 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1, etc. There is a function, and obviously in your mind you should be seeing a bunch of dots that grow really fast. Factorial function grows really fast. But there is a function called the gamma function that matches all those values, but also gives you values for in-between numbers, like 3.2 factorial. But you can't conceptualize that as a repeated multiplication. Can't do it. So at this stage, what we're going to say is that this limit, when we have to invoke growth rates, we do. If we can't take the derivative of this, we just invoke growth rates. So this is by growth rates. So it's using that growth rate chart. And therefore, is this diverge, converge, inconclusive? Inconclusive. Inconclusive. So divergence tests can find divergence if the limit's not 0. But if the limit is 0, then who knows? Got to dig deeper. And that's what we're doing now. We're digging deeper. Digging deeper. So the harmonic series. Harmonic series is that thing up there that we've already talked about a bunch. In order to look at the harmonic series and prove that it diverges, we're going to do the following. So first off, we always consider the sequence of partial sums. We find S sub n. If we find S sub n, then we take its limit. Well, that S sub n we can't come up with a formula for. Like telescoping, we had all the cancellation, and we could come up with a formula that we could take the limit of. There's no way to write this without the dots. We can't add that up and get a closed form for S sub n that we could then take the limit of. So we cannot just take the limit of this S sub n, because we don't have a formula. We don't have a way that gives us the nth value by just plugging in n. Like with the telescoping, we ended up with S sub n equals a polynomial looking like thing that we could take the limit of. We can't do that here. But what we can do is look at some geometry from the graph of 1 over x. So here's a picture of 1 over x. We want to try to understand geometrically what S sub n is. S sub n is those n numbers added together. Here's a visual. The green rectangles from 1 to n plus 1 represent those n terms. Everyone okay with that? So the first rectangles between 1 and 2, the second rectangles between 2 and 3, the nth rectangles between n and n plus 1. So the left endpoints are counting up to n, but then we need the right endpoints to finish off all the rectangles. So there are n rectangles there. N rectangles. Clearly from looking at the graph, if you add up the n rectangles, that is more than the area beneath this curve from there to there. That's what this is saying. Right? The sum of the rectangles, which represent S sub n, that's more than what's underneath the black curve. You agree? Right? Those rectangles are overestimating the area beneath the curve. So this statement is true. S sub n is bigger than the integral from 1 to n plus 1 of the function 1 over x dx. So then let's look at that integral. Well, that's an easy integral. It's just a natural log. And so we get natural log of the upper limit of integration minus natural log of the lower limit of integration. That's 0. So S sub n, so this tells us that S sub n is larger than natural log of n plus 1. That's what that's saying. The green rectangles add up to more than what's underneath the curve. Now to find S, we take the limit of both sides. The limit of S sub n as n goes to infinity. Well, the limit of natural log of n plus 1 as n goes to infinity is infinite. And S sub n is bigger than it, so it's also infinity. So therefore, diverge. So the harmonic series diverges because its sequence of partial sums gets arbitrarily large. The limit of the sequence of partial sums is infinity. So if the sequence of partial sums goes to infinity, then the series diverges. Series must diverge. So that shows us that the harmonic does diverge. This is going to lead us to our next test. So now we have geometric, we have telescoping, we have divergence test. Next test is going to involve an integral. So here's our next test. I think we have 10 total, if I remember properly. The next test is the integral test. So the integral test says, and this should remind you of what we did on the last test, the improper integration. It's not going away. If we take an infinite series and we find the corresponding improper integral that has the same function, so the function creates these a sub k's. So in the last one, the f of x was 1 over x, because the a sub k was 1 over k. So we find the corresponding function. If you can integrate that corresponding function, like we could with the 1 over x, integral of 1 over x is natural log of x, absolute value, then both of those things, the infinite series, the improper integral, they both do the same thing. They either both converge or they both diverge. It does not tell us what the series converges to. But if we can find the associated improper integral and that associated improper integral converges, then the series converges. We just don't know what it converges to. So here is the idea. And in the case of convergence, this integral, we already know how to evaluate improper integrals. We did that a lot. The value of that improper integral is not the same as the value of that series. There might be oddball situations where it is, but in general, the value of these two, if you have convergence of both, is not the same. All right. So let's look at this rectangle thing again. So we have n rectangles right here. Actually, we have n minus 1 rectangles, I should say. Because this one is going to go from 2 to infinity. 2 to n. 2 to n. So this is n minus 1 rectangles. If we wanted to know what the number of terms here was, if we subtract 1 here, we get 1, but then we subtract 1 there and we get n minus 1, that would tell us that we have n minus 1 terms. So here's a picture of those n minus 1 terms. All right, there's a picture. These n minus 1 rectangles are underestimating the area beneath that curve. The integral from 1 to n is the area beneath that curve. right there. That is underestimating it. And if we shift and use the same n-1 rectangles, but we shift them and use, let's see, this interval, didn't we use a right endpoint? So over here, instead of using the right endpoint, we're going to use the left endpoint. So it's a left endpoint approximation. This left endpoint approximation, we still have n-1 rectangles. We still have n-1 rectangles, but those n-1 rectangles overestimate the integral from 1 to n. Okay, so squeeze theorem, we've got an underestimate and an overestimate. And the idea is if we take the limit of both of those, and they are the same, then the middle one has to be equal to that. So that's the idea. Okay. All right, so the integral test says that if these both are converging, then the thing in the middle must, if this thing here converges, if the integral converges, then both of these guys are going to converge also. All right, it's going to be a squeeze theorem type of thing. So that's what the integral test says. The integral test is going to say, if we can find the integral of this, it's going to be bigger than this partial sum. And if this is finite, then that partial sum must also have a finite limit. So let's try it. So we look at this. It's not geometric. It's not telescoping. If we think about the divergence test, what's the limit of a sub k? 0. Limit of this is 0. Numerator is 1. Denominator is going to infinity. Fractions are going to 0. So divergence test, inconclusive. So now we're at our fourth test, integral test. This function, can we integrate it? Yes. Let's use the integral test. So that's going to be sort of our process of triage. One thing at a time. Okay, it's not geometric. It's not telescoping. It's an inconclusive divergence test. So can we integrate it? Yeah, we know how to integrate that. So we are going to integrate from 1 to infinity. And I will always convert to x's here. You don't have to if you don't want to. So we have that. We have that improper integral. As we learned from the last test, the very first thing you should be writing down is limit. The way you evaluate an improper integral is to take the limit of a definite integral. So we're going to create the definite integral from 1 to b. And we're going to write this as 2x plus 4 to the negative 2 dx. Power rule. So we still have a limit. Power rule, we add 1 to the exponent. We divide by the new exponent. And then we do reverse chain rule. Reverse chain rule is division, not multiplication, by the derivative of the base. And then this is from 1 to b. All right, so we could rewrite this, which I highly recommend. Rewrite this before you do your limit evaluation. It's way easier, and we can even pull the constant out in front. It's way easier to evaluate limits when you have positive exponents. So this is going to be 1 over 2x plus 4, 1 to b. Pull out the constant. Get rid of the negative exponent. This is going to end up being the limit, whoops, negative 1/2 times the limit. Negative 1/2 times the limit of 1 over 2b plus 4 minus 1 over, plugging in a 1 right there, we get 1 over 6. So I'm going to take that limit as b goes to infinity. And that first fraction, yep.
The negative 1 times 2 that is in the denominator of the 2x plus 4 to the power of -1. Is that the exact same thing as just saying -1/2 from the integration?
Mm-hmm.
Okay.
Yep, exactly. So this 2 is in the denominator, so it comes out in the denominator, and the minus sign, you could have it in the denominator, you could have it in the numerator, you could have it in front.
Okay.
The minus always has 3 places it can live. Top, bottom, or front. And what does this first fraction go to?
0.
Yeah. So our overall limit is -1/2. The limit of a constant is itself. So we have 1/12. So that tells us, because this is a constant, it's not infinity, this tells us that both the improper integral and the infinite series converge. Okay? So, and there's several ways you can indicate this. I like to write the following. This is an element of the reals. So that epsilon stands for in math element, E, Greek letter E, epsilon, element. This is an element of the reals. Therefore, both converge. So that's how I'll tend to write it. So if you do the improper integral and you get a number, that means the improper integral converges. If the improper integral converges, the integral test says then the infinite series also converges. So both converge. What I mean is that the improper integral and the series both converge. So that's the integral test. It does not tell us that the sum of the series is 1/12. Might be close, but it's not the sum of the series. Let's try another one here. So we look at this thing, not geometric, not telescoping, divergence test is inconclusive because the limit of that is 0. The denominator is growing without bound, numerator is constant, so we're in the same boat we just were in. We look at that and we say, oh yeah, we can integrate that. We can use substitution. Substitution, you generally are picking what's in the parentheses, but that only works if the derivative of what's in the parentheses is present. The derivative of ln k is 1/k and it's present. So substitution works if the derivative of the natural choice is present. So let's go ahead and try to integrate. So we're going to take the limit as b goes to infinity, integral from 2 to b, and I will convert these to x's. So there is the associated improper integral. And we're going to use u sub. So if we let u be ln of x, the derivative of ln of x is 1/x dx. Then substitution is going to work just fine. So we're going to have a limit of, let's see, we get u squared in the bottom. Right, u is natural log of x, so this is a u squared, but then the 1/x dx becomes du. So we're going to have integral, that's just a du. And now we could convert our limits, or we could go back to the original limits. I'm going to choose to go back to the original limits. So I'm going to just pick some placeholder limits. We have that. We're going to rewrite this so that we can use the power rule more easily. So this is our integral. And that's a pretty easy integral. We add 1 to the exponent, we divide by the new exponent, so we get u to the -1/-1, which we can probably all write that as -1/u pretty easily. And then we want to get back to our original and use our original limits. For these types of problems, it's always easiest. So we're going to have the limit of -1 natural log of x. We could factor out the minus if we want. That's a simple enough constant, we can probably just leave it. And this is going to be 2 to b. plug in the b, we get minus 1 over natural log of b. Minus a minus is plus 1 over natural log of 2. We're taking the limit of that whole thing as b goes to infinity. And what is true about this very first fraction right there? Where does that go? 0. Natural log of b, as b goes to infinity, the natural log function grows without bound. So 1 divided by a function going to infinity goes to 0. So that's going to 0. So that's going to go to 0. Therefore, our limit is 1 over natural log of 2. This is a real number. Therefore, both converge. So that means the improper integral is converging and the series is converging. So both have to do the same thing. Both have to do the same thing. Any questions on any steps there? We can kind of see with this integral test that the improper integration is very closely related to infinite series. Because when we do an improper integral, we're thinking of an infinite number of rectangles added together. Yeah?
Remind me, what are the 4 different tests that we can use depending on the situation of these kind of problems? So it was like geometric.
So far?
Yeah.
So far we've had geometric, telescoping, divergence test, and integral test. I think we're going to have a total of 10. You can look on that handout that I've got them all listed out. I think there's 10 total. So, let's go here. All right, so you all try this one. So number 26, you guys try that. It's not geometric, it's not telescoping, divergence test is inconclusive. So integral test is the next thing. Integral test.
Just like 1/2 outside.
In terms of building up your intuition, what's your intuition? Should this converge or diverge? Let me look at that. If the top is a quadratic and the bottom is a cubic, what is it acting like? Like a 1 over k? Right? That 5 in the bottom is really insignificant, just adding a 5. So it really acts like k squared over k cubed, which reduces to 1 over k, which we already know is the harmonic, which diverges. So we should be confirming divergence here. That's, knowing where you're going is very helpful. So in your mind, you should sort of be thinking, oh, I'm trying to confirm divergence using the integral test. And as you're looking at that integral, what form is that integrand in? Almost. It's almost in, it's almost in log form. So it's log form-ish. You have to multiply top and bottom by 3. Right? Derivative of the bottom is 3x squared or k squared. So if you multiply top and bottom by 3, then it's in log form. And once it's in log form, we're off to the races. We can factor the 1/3 out to the front, and we have the limit. And then if it's in log form, we get natural log absolute value of the denominator. And that'll go from 1 to b. So log form, the derivative of the denominator, if it's the numerator, then it's in log form, and you get natural log absolute denominator. So then we have 1/3 limit. Natural log of b cubed plus 5 minus natural log of 6. And this limit is as b goes to infinity. And that limit is
Infinity.
infinity. Right, once again, natural log. If the inside of the log is going to infinity, the y values of the log are going to infinity, so that diverges. So that's going to be infinity, so therefore both diverge. So both the infinite series and the improper integral diverge. Okay, they're getting silly on us down here. So we know that 1 over k diverges. We know that 1 over k, ln k diverges because we looked at that somewhere along the way. Now the question is, if we make the denominator increase a little bit faster, is that enough to get convergence, or is it still going to diverge? So it's not telescoping, it's not geometric. The divergence test is inconclusive because the limit is 0. So integral test, that thing is integrable. Is it though? I think yes. I think yes. Let's find out.
The double natural log is throwing me off here.
Yeah, it should, because it's not very nice.
Oh, no.
Okay, so the first question is, whatever you choose for u, if it's going to work, the derivative of u has to be present. When we look down here in the denominator, certainly if we let u equal ln of x, 1 over x is present, so that seems like a plausible choice. But it's not really going to work because then we're going to end, well, it could work. Then we're going to end up with u ln of u, and we're back to where we started again, and we'd have to let u be, we'd have to use another u, like a v, to equal natural log of u. So what we're going to do is just try this one. What about if we do that? If we let u be that, will we get a function that's present? Let's just check. So we're going to pick the most complicated thing in the denominator, the thing that we like the least in the denominator, that thing. So this is ln of x. So the outer ln, the derivative of it is 1 over the inside. 1 over the inside multiplied by the derivative of the inside. And the derivative of the inside is 1 over x. So this turns into 1 over x ln x. Oh, that's present. Right, that's present in the integrand. 1 over x ln x is right there. So we can use regular substitution just once. So we're going to pick asterisks, representative limits of integration, temporary limits of integration. We're going to go back to the original. So let's see. dx divided by x ln x, oh, that's all du. And down here, that's u. So we end up with du over u. All right, and we know that, what's the integral of d over u? ln of u. So ln absolute value of u.
Are you kidding me?
Right? Yeah, exactly. This is going to get really silly. So this is going to be limit of ln of absolute value of u, but u is ln x, so this is ln x inside of ln, which means ln x. And if you want parentheses here, just to, if this helps, you can do this kind of ridiculous thing. That makes it easier. And now we're back to our original limits of 3 to b, and our limit is as b goes to infinity. So let's see, so we're going to have the limit as b goes to infinity of ln b minus ln of 3. And what is that limit as b goes to infinity? Infinity. Still infinity. Still infinity. Therefore, both diverge. Both diverge. So that didn't increase the denominator. The denominator is not going to infinity fast enough for this to converge. All right, so they both diverge. Okay, new series, number 5. This one's the best. Most people love this one. This one's easy-ish. This should remind you of improper integration pretty much exactly. We already saw this. When we did improper integration and we were analyzing a power of x in the bottom, in the denominator, if the power on the x were bigger than 1, the horizontal tail was finite. That's what a p-series is. A p-series is analyzing the power of the denominators k or whatever it is, k, n, x, whatever it happens to be. So that is the form of a p-series, 1 over k to the p. So we want to massage our integrals, or I should say summations, so that we can put them in this form, 1 divided by k to the p. Just like we had them over here, 1 over a power of x. If we can get it in that form, then all we have to do is look at the power. Power bigger than 1, converge. Otherwise, diverge. So this is improper integration, just like we did in the prior test. So here we look at forcing the numerator to be 1. If we are going to put this in p-series form, we need to force the numerator to be 1. So we're going to shove that power of k down in the denominator by turning its exponent negative. So we have that. All right, we're still not in the proper form. It should be k to a power, not k to a power times k to a power. It's close, it's ish, but we're not there yet. This is going to be k to the, we add the exponents so we get that. I'm going to use some shorthand over here on the summation. We know that these are all infinite. If you just put the low number here that you're starting with, it's understood that it's from 2 to infinity. If you want to abbreviate a little bit, you can. We've already established that this is going from 2 to infinity, so if we put the 2 there, we know we're starting at 2. All right. Now we have rewritten it so that it's in the form of a p-series. We identify p. So on your exam, I need to know at this point that you're identifying it as a p-series. So you somehow have to say, if you say p equals, then I know you know it's a p-series. You've got to make sure you show enough work so I know what you're thinking. So that's the p. P is that exponent. Now we have to decide, is that bigger than 1 or not? Is that bigger than 1? Is pi minus e bigger than 1?
Yes, wait. It's positive.
It's definitely positive.
It's like, I don't remember what e is.
Is it bigger than 1? No, not bigger than 1. So this is not bigger than 1. This is less than 1. Therefore, we have divergence. Yeah. 3. So if you think about decimals just a little bit, 3.14 minus 2.71, then that's definitely, it's less than 1 apart. Yeah, so less than 1, so that's going to diverge. The only way it can converge is if that power is bigger than 1. All right? All right, you all try this next one. See, put it in the put it in proper P-series form and analyze your P. See if your P is bigger than 1, less than 1. If P is equal to 1, then it diverges too. But usually it's bigger or less than. P equals 1, then you have the harmonic. Let's see.
So doesn't the numerator have to be 1, or it could be?
So if there's a constant here, you can always factor the constant out to the front of the integral, or the summation. Because we know that if we have a series and we multiply by a constant, that multiplication by a constant doesn't affect convergence or divergence. So that's going to be the first thing you're going to do is get that out of the way so you can have a constant multiplied by a P-series. So that's what you should have as your next step. The constant can come out. Constant multiplication doesn't change convergence or divergence, so somebody tell me what P is.
3x.
And is that bigger than 1 or less than 1?
Bigger than
Do we have convergence or divergence?
convergence.
So that's it. So that's the work you would want to show. Rewrite it, identify P, compare it to 1. If it's bigger than 1, make your conclusion that it converges. If it's less than 1, make your conclusion that it diverges. So P-series are pretty straightforward. Let's take a look at this one. So they're just being cheeky here. We can take the third root of 27. The third root of 27 is 3. And then the third root of k squared means k to the 2/3 power. So it's not written exactly as a P-series yet, it's ish. So we're just going to factor out that constant. Factoring out a constant does not change convergence or divergence. Now we've written it as a constant times the P-series. We know that the constant is meaningless in terms of convergence. Now we have to identify P, and P is 2/3, which is less than 1, therefore we have divergence. So the P-series test is pretty nice. Come on.
I just kind of rewrote it to look at it differently.
Mm-hmm.
So
Yes.
that's what I did. But
Yep.
it's still.
Well, this is not still written in the right form, though.
Oh, is it?
So it's gotta
is it
be-
that version?
Yeah. So we have to multiply there. So to get it in the proper form, we have to get k raised to a constant. We don't want a constant to a constant. If we have a constant to a constant, we can multiply the two constants together. And that's what I did right here. So this is k squared to the 1/3 for sure. But that's not P there. We have to combine those first. When you have a power to power, you multiply. So that'll be your P. So you want to get it to the point where it's k raised to a constant power. K to a constant. P-series. We love P-series. Okay. Choose your test. This is always the hardest. On the exam, I will be explicit and say use. If I don't tell you what to use, you can use anything you want, but like for the ones that are integral tests, I'm going to say use the integral test. Because it can get really, if we have 10 different tests, trying to triage your way through is a little complicated. But it's a very good exercise to try to get yourself to go thinking about each of the tests and which one is applicable where. The first test, though, we always ask ourselves, unless it's obviously geometric or telescoping, the first thing we always say is divergence test. So we take the limit of base of k. What's the limit of base of k here? limit is. Did I hear something? It's 1. Okay, so let's go through the math. So the limit of a sub k, the square root symbol is a continuous function. Limits can be, whoops, that's as k goes to infinity. Limits can push through continuous functions to the inside. So if we wrote down every gory step here, we would push the limit to the inside, and we would have that. The limit of a square root is the square root of limit because the square root's a continuous function, so the limit can push to the inside. And if you write down every gory step, then you distribute the limit to the numerator, distribute it to the denominator. If you wanted to get really silly, you write down all these steps. And so we get infinity over infinity, you know, and we would do L'Hopital's rule, or we could do split the fraction. You know, there's a lot of ways that you could do this. So if we split the fraction, we end up with that. If here you said, hey, those are polynomials of equal power, then you take the ratio of coefficients, which is 1. So you can do the algebra technique, you can do a calculus, it doesn't matter. In the end, you get 1. So what does that tell us?
Nothing.
What? It tells us everything.
Oh, a divergence.
Divergence.
Okay.
Yeah, if this limit is not 0, therefore we get divergence. So the divergence test can tell us divergence. It can't tell us convergence, but it can tell us divergence.
On the second step, when you put in the limit of k plus 1 over k inside the square root, couldn't you also divide it by k since they're both infinity over infinity? So then that way, it's basically going to be 1 over 1. Square root of 1 is just equals to 1.
Right, and that's what I did here. I divided by k.
Okay.
So that's what I ended up, because here it's indeterminate, it's infinity over infinity. So here, so that means we have to reevaluate. And so the reevaluation can be done by looking at the powers being equal and taking the ratio of leading coefficients. Or you could divide by the k. Or you could take the derivative of the top and the derivative of the bottom and get 1 over 1, which is 1.
Okay.
So there's always 3 ways to evaluate these limits. Algebra, calculus, and some other type of calculus. Multiple calculus ways. All right, that one. Next one. Definitely not geometric, right? Geometric, you should have a power. Right? Geometric is a power, like r to the n is a power, or arc, r to the k, ar to the k. It's not geometric, it's not an ar to the k, it's not telescoping, there's no minus sign. Can we integrate it? Yes, yeah, we can integrate it. That's an arctan-ish thing. Divergence test is inconclusive because the limit of a sub k is 0. So this is going to be an integral test. So we're going to say, let's consider the integral. We're going to take, and we can jump to the limit right away. Limit as b goes to infinity. We're going to go 0 to infinity of 10 divided by x squared plus 9 dx. So that's integral test. Well, we are going to factor out the 9. We can factor out the 10 also. Whoops. So I'm going to factor out the 9 to the front, the 10 to the top, 9 to the front of the bottom. And then we're going to have dx in the numerator. Downstairs, if we factor out a 9, there's no 9 there, so we put 1 there, and it turns into 3x squared plus 1 from 0 to b. I already put in the limit symbol, so that should be a b up top on this first integral. And now it's arctan. Now we have arctan form. That's our basic arctan integral. Right, 1 over u squared plus 1, x squared plus 1. We just have to reverse chain rule it. So the 10/9 can come to the front of the limit. Or you could think that the limit's going inside the 10/9 because that's a constant being multiplied, which is a continuous operation. Limits can float through continuous functions. So this is going to be arctangent of 3x.
Is it 3x or x over 3?
It is x over 3, thank you. Thank you. It is x over 3. Thank you. Yes, 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 yes. So arctan of x over 3. And then what do we have to do? Divide by
1/3.
1/3, which is the same thing as multiplying by 3.
I was right.
Yeah. You're
I
right.
did the other, well, I did the other way, the 1 over a.
Oh yeah, that would also work. So then this is 0 to b. So the 3 can factor out there, so we're going to be left with 10/3 in front. And then limit of arctangent of b over 3 minus arctangent of 0. And that's as b goes to infinity. And what's arctangent of 0? That's equal to 0. Arctan goes right through the origin. It's that sideways S thing. So what is the limit as b goes to infinity of this arctangent piece right here? Where does this go? Pi over 2. Right? Arctangent has a horizontal asymptote on the right at pi over 2. So our answer here is 10 pi over 6, but the 2 cancels, so we get 5 pi over 3. So that tells us that the improper integral converges. This is a real number, so it's an element of the reals. And if that's a real number, therefore both converge. So that series converges, which should fit our expectation, because adding 9 in the denominator is insignificant. Multiplying by 10 in the numerator is insignificant. So this should act like 1 over x squared. 1 over x squared is a p-series that converges. It's also an improper integral that converges.
So the inverse of tangent to infinity, it's pi over 2. So if it was negative infinity, would that be negative pi over 2?
Yes, negative pi over 2.
Okay.
Yep. So if we look at that graph of inverse tangent,
It goes from negative pi.
the graph of inverse tangent has those 2 asymptotes. So if we're going to positive infinity, it's at pi over 2. If we're going to negative infinity, it's at negative pi over 2.
Would that also apply for sine and cosine?
No.
No.
Inverse sine and inverse cosine?
Yes.
No.
No. Okay.
Yeah, those have totally different graphs. Yeah. Yeah, the inverse tangent shows up a lot because it has this limit. Inverse sine and inverse cosine actually, they're not defined outside of negative 1 to 1. So, yeah. All right, should we stop? Let's stop. We'll take a break. Take a big break
Till Thursday.
till Thursday.
Sorry, ask.
What are we in week 10 now or something?
I don't know.
Something ridiculous? Double digits?
Yeah.
Week 10, right? It starts today.
Yeah.
Week 10 starts today.
No, I understand that.
So if you have questions, stick around. I will stay as long as you need me to. We can go over anything you want.
Sure we can last.